Okay, in this video we'll be looking at 2D momentum, and just a recap, momentum, as we know, is a vector quantity, so we symbolize that with the little hat on top of the symbol, and this is equal to the mass times the velocity, and we know velocity is also a vector, so we also put that little hat on the velocity symbol as well, and therefore this gives momentum units of kg meters per second, right? And so if we have an object and it weighs 10 kgs, it's moving at 2 meters per second, then we know the momentum can be calculated by its mass, which is 10 kgs, times its velocity, which is 2, and so its momentum is 20 kg meters per second, right there. And we know the direction is to the right because the velocity, which is the vector, is going to the right. Okay, so just to recap, let's look at some collisions in one dimension. So when we mean one dimension, we only mean across the x-axis or across the y-axis, so either to the side or up. And so if we have a mass, let's call this m1, and it's moving at a velocity, let's call this v1, and we have m2, which is a stationary object. So this is before, right? And then after they collide, we have that same m1, and now it's combined with m2, so they've stuck together, and now they're going off at a velocity of v2, let's say. And so due to conservation of momentum, v1 is greater than v2, as the total mass of this is now larger, because it's now m1 plus m2, whereas the mass of this is significantly smaller, because it's just m1. So from this we can gather the law of conservation of momentum, which is, so in a closed system, momentum is conserved provided there are no external forces, aka it's a closed system. And so another key idea here is that at any moment, we can imagine the center of mass of this system, which will probably be, let's say, around here, because m1 is much larger than m2, so it'll be closer to m1. And so let's say that center of mass is there, that's the center of mass. And so this center of mass is moving at a velocity. It is not the same as m1. It's actually going to be slower. So that will be, let's call that v3. And so that's where the center of mass is before the collision. And so after the collision, it will probably be somewhere like here. So again, still closer to m1, but more in the middle because m1 and m2 are together. And so that's the center of mass. But that center of mass is still moving, let's draw a line, it's still moving at a velocity v3. And so this is actually another way of stating the conservation of momentum. We can say that the center of mass of a system follows Newton's first law, right? And just to recap, Newton's first law is an object will either remain stationary or continue at a constant velocity unless acted on by a net force. And so we know if there is a net force present, then there must be acceleration due to Newton's second law, which is A is F over m. So that is all of level 2, right? So in level 2, we only focus on one-dimensional momentum. However, in level 3, to solve the collision problems, we would have to use Pythagoras and also our trig, and we will be using these using vectors. Right, so we know momentum is a vector, and so we will be drawing some vector triangles to calculate the momentums, and therefore we can get either the mass or the velocity of an object from there, essentially. So let's look at an example. We have a V4 collision, right? Let's say we have an M1 and it's moving at a velocity V1, and we have an M2. Again, this is stationary. And in our after scenario, we will have M1, not quite the same size, but it doesn't matter. And we will have our M2, and so M1's moving off in this direction, and M2 is moving off in this direction, and this forms a right angle between them, and we can call this V2 and this V3. So in order to solve this, we would first use our conservation of momentum, therefore the momentum initially is equal to the final momentum, and so P initial will be the total momentum of this system in the before state, and so we can say pi is equal to m1 v1. Again, because momentum is mass times velocity, and because m1 is the only object moving, so m2 has 0 momentum, and so the total momentum is just the momentum of m1. And so our pf, momentum, our final momentum, is equal to m1 v2. So it's the momentum of m1 plus m2 v3, which is the momentum of m2. Now again, as we're working with vectors, we can't just make m1, and we cannot just do this. This is not allowed, as we're dealing with vectors, so they're not scalar quantities, so they have direction, and we need to take that direction into account using our trig and Pythagoras. So this is not good. We scribble that out. Okay. So instead, we need to create a vector triangle. So we will have our initial vector. This is our pi, and that can be written as m1 v1 because that's what we calculated over here. And as our pi is equal to pf, we know that our final momentum has to close this vector. We have our momentum of m1 going up this way, and so we can draw that right there. And we have our momentum of m2 going down this way, so we can draw that right there. And so this is our m1 v2, and this is our m2 v3. And again, this right angle comes in handy because that is our right angle there. There we go. And so now we have a right angle triangle, and so we can use our trig and our Pythagoras to solve this. And so if we just create some values here, we can say that m1 is 60 kilograms, m2 is 50 kilograms, v1 is 1.8 meters per second, and v2 is 1.1 meters per second. And so what we want to find, so our question is to find v3. And so this is our unknown, so we're trying to find the momentum of this vector right there. So we can use our trig for that, so we know that a squared plus b squared is equal to c squared, where this is our c, this is our a, and this is our b. So rearranging for b, we can get b squared is equal to c squared minus a squared, and so b is equal to the square root of c squared minus a squared. m1 v3 is equal to the square root of m1 v1 squared minus m1 v2 squared. Right, and so chucking in our values over here, we get m1, which is 60 kgs, so 60 v3. Sorry, that's m2, not m1. Whoops. Sorry about that. So that's 50 kgs, 50 v3, right? And that's equal to the square root of 60 times 1.8 squared minus 60 times 1.1 squared. So 50 v3 is equal to 85.5. And so v3 is equal to 85.5 over 50. And that's equal to 1.71 meters per second. And so that's the velocity of v3. Okay, so hopefully that helped with understanding 2D momentum for level 3 mechanics. A few other examples that you will need to know. So example 1 would be what we just did, where we have a moving object with a stationary object. So that's our before. And our after would be what we just did, where one moves off this way and one moves off that way, and we have an angle between this. It might not always be right angle, but usually it is for level 3. Probably if the angle isn't a right angle, that's probably more scholarship rather than level 3. It will usually be right angles, I think. We have another very similar scenario. So example 2, where we have a massive object, and then it breaks up into two small objects, one going this way, and the other going that way. So that's very similar to this whole scenario right here. And then we have our final example. Example 3 would be kind of the reverse of the other ones, where we have two objects going this way. Again, extrapolate that. That's a right angle between them, if I can draw that properly. There we go, that's close enough. And then they join together and move off, sticking together. Okay, hopefully that helps.